In this clip, we have a brief proposition that basically just allows us to shift our perspective on when we have a basis giving us an upper triangular matrix. So for an operator T on V and basis V1 through Vn of V, the following are equivalent. So first off, the matrix of T with respect to this basis is upper triangular. This is equivalent to the idea that TVJ lies in the span of all the vectors that we've seen up to this point, and that's true for every j. And that the span of V1 through Vj is invariant under T. So why are these three things equivalent? Well, more or less by staring. So, for instance, if we look at like y is A true if only if B is true, this is clear basically from the shape of the matrix. So if we look at like matrix multiplication, we say, okay, so suppose we've got our upper triangular matrix, and then we've got some vector that has only coordinates in non-zero coordinates at the very beginning, right? So this maybe it's worth pointing out right here that this right here is what it looks like for V to be in the span of V1 up to Vj. So that means that J is somewhere around this coordinate right here. Yeah. So when you multiply these together, you have the same kind of thing that we saw in the previous proposition for why the product of upper triangular matrices is upper triangular. And it's because you're going to be taking, for these lower entries, you're going to be taking, when I say these lower entries, let me explain. I mean, when you're looking at the product over here, so what happens, you're going to get zeros in these same spots down here. And the reason is because of how these row vectors with all those zeros line up with this column vector right here. Yeah. So if you remember that sort of overlapping picture that I drew in the last clip, that will explain to you why you get zeros in the bottom over here. Okay. And then C is true if and only if B is true. And why is that? Well, let's see. So since V is in the span of the foregoing, the V1 through Vj, this is true if and only if V looks like some linear combination C1 V1 up to Cj Vj, and where the other terms have zero coefficient out here, right? And since this expression, this expression basically just shows you that, well, first off, if span V1 through Vj is invariant, then that definitely tells you that T has to map each of the Vj's back into the span. So C implies B. For B implies C, well, if T takes every Vj into the span of V1 through Vj, then T takes any linear combination of the Vk's also back into the span of V1 through Vj. And so that means that V gets mapped back into the span. So the span is invariant under T.